So that's precipitation chemistry. All right, let's do some acid-base. Okay. So the only difference between acid-base reactions and precipitation is that now what you're double replacing involves a hydrogen ion. Okay, when you're moving hydrogen ions around, that's acid-base chemistry. Otherwise, very, very similar to precipitation. Oftentimes, acid-base reactions are called neutralization reactions because you've got some acid and a base, and they react, and they somewhat neutralize each other, oftentimes forming water as a product, which is neutral. Strong acids always produce H plus in water, okay, otherwise called hydronium. The two are very analogous to each other. Hydronium is what you get when the water captures an H plus, whereas H plus by itself is sort of like the hot potato being passed around between water molecules. So both of them are used interchangeably often because of that, but they are slightly different. Okay, strong bases, on the other hand, always produce hydroxide in water. Okay, so if you throw a base in water, you get lots of hydroxide. So that's strong acids and strong bases. There's also weak acids and weak bases. They only partially dissociate in water to produce smaller amounts of hydronium and hydroxide. So even weak acids and weak bases, they will produce hydronium and hydroxide respectively, but in much, much, much smaller quantities. For example, you take acetic acid, that's a weak acid, only approximately 1 out of every million acetic acid molecules will dissociate into hydronium. Okay, so it's very, very mild. Okay. Whereas strong acids, virtually 100% dissociate to water. Strong bases, virtually 100% dissolve into water to produce hydroxide. So we'll go through all these cases. Okay, what is a weak acid? What is a weak base? What is a strong acid? What is a strong base? Okay, how do we identify these? Okay, so we're going to go through that. So you should recognize the strong acids by memorizing the 6 strong acids. Okay, SA means strong acid, so I'm using acronyms here. So memorize the 6 strong acids, and what are the 6 strong acids? Okay, so we got nitric acid, perchloric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. These are the 6 strong acids. How do you memorize these? Did you memorize them for Chem 107? No? You should have. But how would you memorize these? They're so common, it really does, you really need to memorize it. So if you have a periodic table, look at the elements that are unique within the acid. So you got nitrogen. Let's get perchloric acid for now. You got nitrogen, sulfur, chlorine, bromine, and iodine. Okay, these three halogens, along with sulfur and nitrogen, kind of make a squiggly zigzag 7 in the periodic table. So you got, if you look over the periodic table, iodine, bromine, chlorine, and then it kind of skips over to sulfur and nitrogen. Now the oxygen, I'm going to go ahead and use that for perchloric because it has a lot of oxygen in it. So you just look at those elements and say, okay, N for nitric acid, O for perchloric acid, S for sulfuric acid, and then chlorine, bromine, and iodine for the hydrochloric, hydrobromic, and hydroiodic acids. So you always have a periodic table if you want an exam. So I would say try to memorize the 6 strong acids using the periodic table. Right, so it really boils down to okay, so it kind of makes a 7. It's a little zigzag sort of, but right, so it's So you can just, I would say jot that down. Okay, they need to help you memorize those. So the key is to memorize it without really having to go memorize it per se. It's just looking, recognizing the pattern. Okay. So any questions about what the 6 strong acids are? So if you want to know what the 6 strong or what a strong acid is, just know the 6 strong acids. Okay, you can recognize weak acids by any other acid that isn't a strong acid. Okay, it's sort of by default the other way. So examples of weak acids include HF, okay, HNO2, okay, different from HNO3, H3PO4, phosphoric acid, and then acetic acid. Notice how acetic acid, it's an acid, but the H isn't necessarily in front of the formula, but it does have this OOH, okay, and you'll see this type of atomic framework, this type of moieties, they call it, for a lot of for weak acids. All organic acids will have this functional group on OOH. Okay, so if you see OOH, not just OH, okay, a lot of people confuse this with a base, as in hydroxide, but that extra O changes things. So it's actually OOH. As I say, OOH. Okay, so if you see OOH, okay, that's a weak acid. And then of course, if you see an H in the front of the formula, you know it's an acid, but if it's not one of the 6 strong ones, you know it has to be weak. Okay, there are lots and lots and lots of weak acids, okay? So you just have to recognize when you see an acid in general. Okay, so hydrofluoric acid, nitrous acid, nitrite becomes nitrous, right? Nitrous acid, phosphoric, and acetic acid. So those are just a few examples. Strong bases can be recognized by any salt with hydroxide in it. Okay, so if you take sodium hydroxide, potassium hydroxide, barium hydroxide, strontium hydroxide, any soluble salt with hydroxide in it is going to give you lots of hydroxide in solution, and it'll be basic. So notice how this OH on the acid looks way different from, say, hydroxide ion in an ionic compound. So all strong bases are ionic compounds with hydroxide. And then for weak bases, we recognize those by containing some form of nitrogen with hydrogen. Okay, X could even be 0. Okay, but certainly you'll see a nitrogen atom. So examples of that would be ammonia, methylamine. Okay, you don't have to know the naming of the weak bases, except for ammonia. So ammonia, you have to know that. Everything else you can wait till OCHEM to get there. But this is called methylamine. This is called dimethylamine. This is called trimethylamine. Okay, again, there's no H on this guy, right? But he's still a base because he's got nitrogen. So the nitrogen atom tends to be basic. It's got a lone pair on it. If you go back to Lewis structures, and that lone pair likes to reach out and grab hydrogen ions from acids. Okay, therefore it reacts like a base. Going back to any biology course you may have taken. Has anyone ever taken this Bio 101 even? Something like that? Has anyone ever taken any bio at all? Period. Like anybody, right? In high school bio classes, Bio 101, one of the things they always teach you about is DNA in general. Well, what is DNA? It's made up of nucleotides, okay, as in adenine, cytosine, ATCG, cytosine, guanine, and thymine, right? So those are the four main nucleotides of DNA. Every nucleotide is made up of 3 things: a phosphate group, a sugar, and a base. Okay, and then the strands, one from each strand, you get these things called base pairing, right? Maybe A binds to T and C binds to G. Does that ring a bell to anybody from bio? Okay, they call those base pairs. Why do they call them base pairs? They call them base pairs because the base in any nucleotide consists of a couple of rings filled with nitrogen atoms. okay, and the nitrogen atoms make it basic, okay? So that's where the term base pair came from, because nitrogenous bases are in general bases, okay? So biology is absolutely beautiful if you look at it from a chemistry standpoint. When you're studying biology, you're studying chemistry, okay? But a lot of people take bio first, so it makes it really difficult. So just to connect the dot to another class. So the bases are nitrogenous, okay? Those are weak bases. So I think this is a really good slide for you to study, you know, just to keep the big picture in your mind is identifying what's what. Acid-base chemistry, probably the most difficult type of chemistry to study because you have to recognize your players. And I think this slide really summarizes who your players are quite nicely, in my opinion. Okay. Any questions? Now, sometimes you'll have a compound that neither is acidic or basic. It's considered neutral. Okay, it doesn't contribute much in the way of hydroxide or hydronium, or negligibly. So sometimes you have salts without hydroxide. So take, for example, sodium chloride. Okay, if I mix a solution of sodium chloride, or if I go into the ocean, do I get burnt from acid or base? No, I don't, because it's a neutral solution, but it has sodium chloride in it. So there are a lot of salts that are considered to be neutral salts, or even we title them as neutral salts. So sodium chloride, potassium nitrate, magnesium perchlorate, lithium sulfate. The anions in these salts come from strong acids. So whenever you have an anion that comes from a strong acid, one of the 6 strong acids, if you have a salt with the anion from that strong acid, it's going to be a neutral salt. Okay, typically. All right, so these look different from what we've talked about already, right? They kind of look different. Then we also have some organic compounds that do not have the nitrogenous group or the OH. So you take, for example, alcohols. Okay, alcohols, when you get to OChem, they'll tell you they're slightly acidic, which they are. But for the sake of our state, you can assume it's neutral. We've got this kind of compound here. This is called an ether. Okay, these are just organics, okay? Organic compounds, oils, okay, are neutral. This compound is called an aldehyde. Okay, you get CHO. What this is a C double bonded O to it, and then the H is directly on the carbon. Right, so it's not like H is in between 2 atoms, because we know hydrogen only makes 1 bond. But those are called aldehydes. Don't worry about the nomenclature for the functional groups at this time, but just know that we have organic compounds that do not have these 2 groups on it. Okay, if you don't see those, you see it organic, and you know it's got to be neutral. It can consider to be neutral. All right, here's a diol or an alcohol with 2 OHs on there. How can I tell this or this from like a strong base? How can I tell the difference? Because I can guarantee you, probably a couple of you at least in here, will look at OH and oh yeah, it's a base. It's a base. Okay, but what is the OH bonded to for a strong base? It's salt, right? It's a hydroxide salt. Okay, these are not salts. Okay, they're just organics. Okay, they do not dissociate into water and create ions in solution. Okay, they don't do that. Okay, so that's how you can tell the difference. If you see hydroxide bonded to a metal, then it's a salt. Okay, if you see OH and it's got a lot of carbon and whatnot, that's not a salt, right? So that's how you can tell. Okay, there are other organics too, but that's just a list of few. So now that we've gone into identifying our players, let's, oh, here's one more. This is called an ester, okay, but same thing, okay, just looks different from what you've seen. So let's practice identifying these. Okay, we got compound number 1, is that acid base, weak acid, weak base, or neither? Okay, that's a strong acid, right? So that's a strong acid. Lithium hydroxide, what is that? That's a strong base. Okay, sodium bromide, what is that? Neither, right? Neutral salt, or neither, Na. What about the next compound? That looks kind of weird, huh? I heard a murmur of a weak acid. Anyone else agree with that? Weak acid? You'd be right. It is a weak acid. In fact, that compound is called oxalic acid. C2O4, H2C2O4. So that's oxalic acid. All right. Can everyone see why that's a weak acid? You see the OH in there? And there's actually two of them. Some of you might be wondering, how come they've got H and then OO, and here they've got OO and H? Like, why is it reversed? Okay, it's just because in the structure, the carbons are bonded. Each carbon is bonded to two oxygens, and then the hydrogen is bonded on the outside. Okay, so if you got two ends of that, that's why it's written like that. So that's a weak acid. What about H2S? What kind of compound is that? That's a weak acid too. Okay, name of the acid would be called hydrosulfuric acid. Sulfide gives you hydro and hic, so hydrosulfuric acid. Next compound, what is that? Oh, you had a question?
Yes, so for number 4, it would matter about, then you would look at the composition of the,
Yeah, for number 4,
see what it's bonded to? Like,
yeah, I mean, for number 4, you're just looking at the OOH,
okay.
right? If you see OOH, not just OH by itself, but if you see OOH, two O's, then you know it's got to be a weak acid. But if you still only see one oxygen, then you kind of have to look at what it's bonded to. You know, if it's bonded to a metal, then you know it's a hydroxide salt, it's a strong base. If the OH is just bonded to carbon, then you know it's a neutral organic compound. Okay? But that one has an OH, so that's a weak acid. So number 6, what did we agree on? What was that? That's a weak acid, right? Next compound, what is that? That's a weak base, right? So we got nitrogenous base there. Next compound, what would that be? Neither, right? Not applicable. That's a neutral salt. Next compound. Also neither. It's just an organic compound. All right. Last one there. What is that? That's a strong base, right? It's a hydroxide salt. So you see how you can just identify what's what. Once you can identify what your player is, then you can write out the chemistry. Okay. So let's look at the chemistry. Okay. There are 4 possible kinds of reactions you can have with acid-base chemistry. You can have strong acids reacting with a weak base, strong acids reacting with a strong base, weak acids reacting with a strong base, or you can have weak acids reacting with weak bases. We'll get to that in the next slide. Here's an example of a strong acid with a weak base. Okay, so you've got hydrochloric acid, strong acid. Ammonia is a weak base. Reaction would give you ammonium ion and chloride. Okay, how did if you look at ammonia relative to ammonium, okay, what happened to the ammonia? What happened? Did it gain or lose hydrogen? It gained, right? So if it gained hydrogen, why is it now plus charged? What happened there? So it goes back to the question, what is being transferred in an acid-base reaction? In an acid-base reaction, you're transferring hydrogen ions. Another way of saying hydrogen ion is a proton. Okay, H plus is just a proton by itself. No neutron, no electron, just a proton by itself. And so if ammonia just gains a proton without gaining any electrons, okay, it's going to get a plus charge overall. So this is why this is a plus charge. Why is this a negative charge? Yeah, the HCl lost that proton, but the electrons stayed behind. Okay, so now you've got a negative charge on that chloride. So it's really important with acid-base chemistry, not only to move the hydrogen over to the right thing, but also to keep track of the charge. Okay, because you have to understand that it's a proton being moved around. Okay, so that's an example of a weak acid, strong acid, weak base. If we did a strong acid, strong base reaction, this would be our classic example. We have hydrochloric acid reacting now with sodium hydroxide, that's a strong base. And now you're going to produce water. Okay, because the hydroxide, it's going to gain that H+, and that makes water. And now you're going to be left with sodium cation and chloride anion. So when I ask students who've taken Chem 107, this is probably the typical acid-base reaction they remember. Right? Strong acid, strong base, aka neutralization reactions. Any questions so far? So we've got into identifying what our players are going to be. Now we're just going through different chemistries that they take part in. Weak acid with a strong base, an example of that would be acetic acid reacting with sodium hydroxide. So now, this OH, this is the acidic hydrogen here at the end, right? This H at the end. And it's going to be tossed over, the H+ is, to the hydroxide of the sodium hydroxide. And you're getting uniform water. And now we're going to have, instead of sodium chloride left over, we'll have sodium acetate left over. Why is this a negative charge here? It lost the acetic acid lost a proton, but the electron stayed behind. Okay, so now you got an extra electron on that compound. So if you have hydroxide for your base, okay, you're always going to form water. But I think a lot of people, when they're first learning acid-base chemistry, they forget that there are other acid-base reactions that don't necessarily produce water in their net reaction. Okay, okay, so, but hydroxide always gives you water as a product. So we've done strong acid, weak base, strong acid, strong base, weak acid, strong base. What's the one combination left that we haven't talked about? Yeah, weak to weak, okay? Just like you study week to week. Okay, okay, so what about weak and weak? This is the kind of chemistry that you will emphasize much more on in Chem 111B. But just to touch upon it here, this occurs when you have a weak acid or a weak base added to water. Okay, the key underlying word there is weak in water. And these are expressed as equilibria, not as a straightforward reaction. So for example, if I throw ammonia in water, okay, ammonia will mildly dissociate into ammonium cation and hydroxide anion. Okay, so it's a weak base, it does produce a little bit of hydroxide, but again, for every nearly 1 million ammonia molecules, you only get one that actually dissociates into this. And so as a result of that, they use these back and forth arrows now instead of just one arrow going to the right. So anytime you have a weak acid, weak base reaction, it's going to have the double arrows. And the double arrows going back and forth indicate an equilibrium condition. Does anyone remember in Chem 107 they talked about equilibrium? Hopefully a little bit. They should have. If not, you know, now you're seeing it for the first time. But anyway, for acetic acid, that's a weak acid now. Again, same thing, back and forth arrows. This time though, I'm producing a little bit of hydronium, not hydroxide, right? But I'm still getting my anion. So water, is water an acid or a base? Yeah. And it can act as iron, right? In this case, it's acting like a weak acid. In this case, with the acetic acid, it's acting as a weak base. Okay, but water can only act as a weak acid or weak base. It's never a strong acid or strong base. Okay, bases and acids are always measured relative to water. Okay, so when you're dissociating weak acids or weak bases, or even strong acids or strong bases into water, water can act as both a weak base or a weak acid. Okay, so this is in contrast to strong acid put in the water. If I throw HCl into water, it just fully dissociates into hydronium and chloride ion. Or I should say H plus and chloride ion. H plus finds water to produce hydronium. Okay, so those are the different kinds of acid-base reactions. Okay, precipitation may be a little easier because it's just two salts and you're swapping ions. With acid-base chemistry, though, you have to recognize, okay, is it strong or weak and that kind of thing. So how do you write an anionic reaction for an acid-base equation? And the way to do it is that you do not use solubility rules. Okay, that's only what you use for precipitation. So only use solubility rules for precipitation. How can you tell the difference between acid-base and a precipitation reaction? How can you do that? Let me write two possible reactions. Okay, so which one of those is an acid-base reaction, and which one is the precipitation? Yeah, this is the acid-base reaction, right? And this one's the precipitation. So how are you able to tell? Right, so first and foremost, before you get to strong or weak acids, you recognize that this is a base, and that this is an acid. But you recognize that this is also a base. But for this, is this a base or an acid? It's neither, right? It's a neutral salt. So this is just, we'll call it neutral salt. At least for now. In next semester, this might change when we get to other types of acids and bases. But for now, you can just assume this is going to be a neutral salt. So you can see that because there's no hydrogen in this, okay, it's not going to have a Bronsted acid-base reaction with hydroxide. Okay, so can you see the difference? So in order to have an acid-base reaction, you have to have a base and an acid. Okay, whereas if you only had an acid or a base by itself, but with the other one wasn't an acid or base, then it'd have to be something different, right? Okay. So, so getting to net ionic reactions for acid-base, you've got to identify. You have to identify strong versus weak electrolytes, which I haven't given you the handout. Actually, you do have the handout in your problem-solving packet. But excuse me. How do you identify strong versus weak electrolyte? Well, it's just another way of saying identify strong versus weak base, or strong versus weak acid. That's all it is. So once you identify if it's strong or weak, the strong acids or strong electrolytes, or the strong bases or strong electrolytes, are written as fully dissociated ions in solution, whereas the weak electrolytes, aka weak acids or weak bases, are written as being still together. Okay. So I always say